once you learn what the force is on a moving charge when it's in the presence of a magnetic field, and we'll assume that it's a uniform magnetic field. That's typically what we do, kind of an introductory physics or electromagnetism. So when we have that, so you can see that we have the formula right there. You can certainly find out more about this. I can put up a link. I'm going to assume that you are familiar, with a charge which is moving through a magnetic field. Now, we want to be able to kind of point something out, which is definitely very interesting, and it has numerous applications. And that is, if you have charges, so those are any charges, so that you would have. So you have some particular charge. It doesn't matter if it's positive or negative, and it starts to move through a magnetic field. So as you can see here, so the magnetic field is actually pointing, so right out, of the page or right out of the screen. So those are the magnetic fields. So these are the signs for the magnetic field, which is pointing in there. And you have this charge, which is going to be moving, and we're going to make the assumption that it is moving kind of on the perpendicular side. So it's in the perpendicular plane with respect to the magnetic field. So in that case, if it is in a perpendicular plane, then the sine of the angle, so the angle is actually 90 degrees. So this is going to fall off because this is going to be equal to 1. So in reality, our actual force, which is going to be present on this charge, is going to be Q multiplied by the speed that it is moving, and then whatever the strength of the magnetic field is. So that's what we would have on this particular charge, which is going to be moving throughout. So what happens to this charge? Let's kind of take a step by step. At the instant, that this charge is moving at a certain speed, v, so of course there's some kind of a direction, but we are assuming that it's going to be in the plane, then what is going to happen is that the magnetic field is going to cause a force. So we know what that force is, and if this is, let's, for the sake of this illustration, let's assume that it's a positive charge. So we can use a right-hand rule to try to find out exactly in which direction that force would be present in. And in this case, that particular force would have been downwards, and you can convince yourself with the positive charge, or it would have been upwards if it was a negative charge. So that is the force that is present. But if there's a force on this particular charge, then it's going to make this shift over. So it's not going to continue in a straight line. It's actually going to start to bend. And now, so as this thing is moving, so it's going to, as time progresses, so this force is going to try to bend this over. Now, as it starts to bend, and it continues on, so let's say that the charge is now at a little bit further of a distance, so let's say that it's somewhere over here, well, that means that the speed itself is no longer, as it is pointing, but it would have been kind of pointing in this direction, right? So as the charge keeps moving. So that is now the speed, and we're still assuming that it's perpendicular to the magnetic field. Well, so hold on a second. So, we can do a little bit of scratching of heads, and now if we recalculate, so if it's still the same magnetic field because it's uniform, it's still the same charge, it's still going at the same speed, then all of a sudden the direction is going to start to change. So the direction is not going to be downwards because of the fact that it's going to be perpendicular, to this. So now that particular force is going to now switch over, and it's going to be pointing you in this direction. So this is now going to be pointing you in that direction. So that's the force itself. And of course, as this continues, so that means it keeps shifting it over. And what happens is that this charge actually kind of in a nice, unique way, now of course, if you give it enough time, what's going to happen is that this charge is going to find, and it's going to be moving in a circular motion. So if it was all the way at the top, and so let's imagine that it was somewhere over here, the force would have been pointing this in that direction, right? If this particular charge wanted to move in this direction. Now, as it keeps going through, so let's, give it enough time. So if it's going to now shift this over, now this particular charge is now going to be shifting in this direction, and therefore the force itself is going to be now in that direction. And of course, you can continue this process as you're going through, where the force is always going to be trying to pull you, okay, kind of towards the center as you keep moving. So depending on which direction that you are actually going to be moving at. So that is pretty interesting to be able to see that. And we have seen this, and this is nothing else but just centripetal actual motion. So this charge is going to be going in a circle, okay, if you give it enough time, because of the fact that the magnetic field is going to be creating a force on it. And that particular force we can certainly calculate. Now, what does that mean for us? We know what this force is, right? So we have the force, which is equal to this. Now, for anything that is moving in circular motion, we also know that that force, so the net force, is going to be equal to the centripetal force. And that centripetal force is nothing else but the mass multiplied by the speed that it is moving at, squared, divided by whatever radius that we have. Now, that radius is, of course, okay, the radius of the circle that it's trying to create. So that's the radius right there. The mass would have been the mass of the charge. So this will have a certain charge, but it will also carry a certain amount of mass. And then the speed is whatever speed it is moving at. So hold on, we know what these forces are. So we can now equate the two forces. And what we would have, or what we would find, is that we would have that the charge multiplied by the speed times the strength of the magnetic field is going to be equal to the mass multiplied by the speed that it is moving at divided by the radius. And now, if we know the charge, if we know the magnetic field, we know what this is going to be moving at, then we can figure out what the radius that it creates. And it's pretty unique, right? So depending on the mass of that charge, depending on the charge on that mass, it will create a certain radius. And therefore, you can have applications related to this where you can find out, okay, so in terms of certain ions, what the actual radius might be, okay, as it creates. So if you massage this formula, so you will notice that, well, this V will cancel one of these V's, okay, as you're going through, you can now rearrange this. So R is going to be equal to the mass multiplied by the speed divided by whatever the charge and the strength of the magnetic field, and we assume that that is uniform. So you can find out exactly what this radius will be. So for instance, if you have a proton, so let's take this instance, so you have some proton, and that proton, okay, so we know what the charge is, because that means we're just losing one electron. We know what the mass of the proton is, so I've provided these over here. And let's assume, just for the sake of this example, let's take, for instance, maybe the speed, okay, and let's make that speed 2.5, let's say times 10, maybe, I don't know, to the 7 meters per second, for instance. And then we can take that the magnetic field is equal to, and that magnetic field, let's just assume that this is 5 times 10, maybe to the -3, and let's make it Tesla. So now, if you start substituting this back in here, which I will, it would give us what the radius would be. So I'm going to substitute these 4 items back into that formula, and then we'll get what the radius will be for this example. Let's take a look. So here it is. So this proton, it would have had quite a huge radius now for something which is so tiny. But again, so that will be dependent on whatever the strength of that magnetic field is, and then whatever how fast it is moving. If it's not going to be moving as fast, it obviously would have been definitely less. Okay, so in terms of that particular radius. So I hope that this video gives you a sense in terms of trying to tie back in moving charges to centripetal motion, something which you might run into, okay, in studying electromagnetism. All right, so thanks for watching. See you in a future video. Bye, everybody.